One of the classical applications of integration is using it to determine the area underneath the graph of a function, often referred to as finding the area under a curve. For example, let's say we wanted to find the area underneath the graph of the function f of x equals x plus e to the negative 2x between the values x equals negative 1 and x equals 2. The area we want to determine is the shaded region in this graph. Finding the area of such a curved region is tricky. What is a lot simpler is finding the area of rectangles. To that end, let's divide the interval, negative 1 to 2, into two subintervals and approximate the function as being constant in both subintervals. Here we calculate a left-handed estimate, so we approximate the function as being the value at the left side of each subinterval. We imagine the function is equal to 6.39 in the first half, because f of negative 1 is 6.39, and imagine it is equal to 0.87 in the second half, because f of 0.5 is 0.87. For this piecewise constant function, shown by the two blue line segments, it's easy to calculate the area underneath it. The area is just the sum of two rectangles. The width of the total interval from negative 1 to 2 is 3, so the rectangle widths are exactly half that, which is delta x equals 1.5. We multiply the two heights by 1.5 to get the two areas, 9.58 for the first rectangle and 1.3 for the second rectangle. When we sum up these two areas, we calculate the total area as 10.89. Well, I actually get 10.88 when adding up these two numbers, but the computer is doing a more accurate job by not rounding until the end, and it gets 10.89. We could do a similar calculation by approximating the height of the function in each subinterval by its height at the right of the interval, obtaining a right-handed estimate. In this case, the rectangle heights are 0.87 and 2.02. Their areas are 1.3 and 3.03 for a total area of 4.33. These two estimates of 10.89 for the left-handed estimate and 4.33 for the right-handed estimate are pretty far from each other and not too close to the actual area under the function. To improve the accuracy, we can increase the number of subintervals. For 10 subintervals, we obtain estimates for the area of 5.95 for the left-handed estimate and 4.64 for the right-handed estimate. The sum used to calculate the area of the rectangles is exactly the Riemann sum we used to define the definite integral. For the left-handed estimate, we get the left Riemann sum, which is the sum from I equals 1 to 10 of f of t sub I minus 1, which is the height of the left side of each subinterval times the width of the rectangle delta x. For the right Riemann sum, the only thing that changes is that we use the height of the right side, f of t sub I, for the rectangle height. We can increase the number of rectangles to improve the estimate of the area. To get the actual area under the curve, we need to take the limit as the number of rectangles, n, goes to infinity. This limit is exactly the definition of the definite integral. The area under the function f of x, for x between negative 1 and 2, is therefore the integral from negative 1 to 2 of f of x dx, which, since our function f of x is x plus e to the negative 2x, is the integral from negative 1 to 2 of x plus e to the negative 2x dx. We can now jettison our Riemann sums and instead use the fundamental theorem of calculus to calculate the area given by the definite integral. To start, we calculate the indefinite integral, or antiderivative. Let's separate the integral into its two terms. To make the second integral easier, we multiplied and divided by negative 2. We take the integral of x to get 1/2 x squared. The integral of negative 2 times the exponential is the exponential itself, so the second term is negative 1/2 times the exponential. This function is our antiderivative big F of x. We didn't need to add an arbitrary constant c here because we are computing a definite integral. By the fundamental theorem of calculus, the definite integral defining the area under the curve is simply this indefinite integral, f of x, evaluated at x equals 2, minus the same f of x, evaluated at x equals negative 1. We plug in those numbers to find that the area under the curve is approximately 5.185. How does this actual area compare to our estimates with the rectangles? When we have 100 rectangles, the left Riemann sum gives us 5.25, and the right Riemann sum gives us 5.12. These answers were converging to the correct answer of 5.185. We would need a lot more than 100 rectangles to give us 3 correct digits. Thankfully, we can avoid calculating a huge Riemann sum and just calculate the integral directly. Let's do another example. Let's calculate the area between the graph of the function 1 over x and the x-axis over the interval of x from -2 to -1. We begin by calculating the integral from -2 to -1 of 1 over x dx. The antiderivative of 1 over x is the logarithm of the absolute value of x. So, by the fundamental theorem of calculus, we evaluate that logarithm at x equals -1 and then subtract the logarithm at x equals -2. The absolute value eliminates the negative signs, so we have the logarithm of 1 minus the logarithm of 2. The logarithm of 1 is 0, and the logarithm of 2 is 0.693. We calculate that the area is -0.693. Wait a minute, that doesn't make sense. It doesn't make sense to have negative area. Something must have gone wrong here. Let's take a look at the graph of the function to determine what happened. Since x is negative, the function 1 over x is also negative. When trying to calculate the area, we are getting negative heights, so it makes sense that we end up with a negative number. If a function is negative, the definite integral doesn't give us area, it gives us minus the area. This problem is easily fixed. The distance from the x-axis to the function will always be the absolute value of the function, which gets rid of the negative sign if the function is negative. To get the area, we need to integrate the absolute value of 1 over x. When x is negative, what is the absolute value of 1 over x? Since 1 over x is negative, we simply need to multiply by -1 to make it positive. The area is the integral from -2 to -1 of -1 over x dx. We just need to take our previous answer of -0.693 and multiply it by -1 to determine that the area is 0.693. Let's look at one final example. If we take the integral from -2 to 1 of the function 4x cubed minus 16x, we will get a number since it is a definite integral. In terms of area, what does that number represent? For starters, let's go ahead and compute the integral. The antiderivative is x to the 4 minus 8x squared. We evaluate it at 1 and -2 and take the difference. The number we get for our answer is 9. To see what this 9 represents in terms of area, let's plot the graph of the function. In between -2 and 1, the function is both positive and negative. It is positive from -2 to 0, and then negative from 0 until the end of our integral at 1. This means that we are adding up positive numbers for the area from -2 to 0, and then combining that with negative numbers for the area from 0 to 1. What we are doing is calculating the area above the x-axis and then subtracting the area below the x-axis. We call this result signed area. If we don't take an absolute value, the integral of f of x is the signed area between the graph of the function and the x-axis. It is the area above the x-axis minus the area below the x-axis. To demonstrate this result more clearly, let's compute the positive and negative portions of the integral separately. If we compute the integral from -2 to 0, which is where the function is positive, we get 16. The area under the curve for x between -2 and 0 is 16. If we compute the integral from 0 to 1, where the function is negative, we get -7. This means that the area between the curve and the x-axis is 7, but it comes out -7 because the graph is below the x-axis. The signed area is the sum of these terms, which is why we get 9. If we want to calculate the actual area, we have to take the absolute value. The absolute value doesn't change the integral from -2 to 0, as the function is positive there. However, it multiplies the function by -1 for x between 0 and 1, changing the -7 to 7. The actual area between the curve and the x-axis is 16 plus 7, which is 23. In summary, the definite integral of a function f of x will give you the signed area between the graph of the function and the x-axis, subtracting area below the x-axis from the area above the x-axis. If you want the actual area between the graph of the function and the x-axis, you need to take the absolute value. That complicates the calculation a little bit because you have to find out where the function is negative and multiply it by -1 in just those intervals. Even so, using a definite integral is a pretty nifty way to determine the area under a curve.